Heinz 57 sauce brown today. Okay, today we're talking about fluid dynamics, which, if you remember, is what we were going to, talk about yesterday, but ran out of time. Fluid dynamics. Hey, let's break it down. You know how to break it down. What does dynamics mean, probably? This is as opposed to, there's a kind of science called statics, and this is dynamics. What do you think is the difference between those two things? Okay, yeah, that's a good start. Dynamics is referring to how something changes. Or moves. If you have a dynamic personality, that means you aren't just acting the same all the time. You know some people that have a static, monotone personality, where they're just the same level all the dang time.
Wyatt Brady.
Yeah. At Wyatt Brady. No, I'll put that in the comments or in the description. The comments are blocked. Okay, anyway, but a dynamic personality would be one where, like, if something sad happens, you're sad, and if something happy happens, you're happy, and you can change for the, anyway, whatever. Dynamic means that it has the ability to change, and then fluid refers to what? This is related to the Latin word, which fluctus, which means to flow, and this is just any substance that flows.
So a fluid does not have to be a liquid.
Exactly right, Peyton. Say it into the mic. Say it. Oh, I'm just touching the mic. It's gonna sound awful. I saw the meter go. Come here, baby. Okay, Peyton. Say it.
Fluid has to be a liquid.
Okay, that's the opposite of what he said before. Say the other thing.
A fluid does not have to.
Okay, that one's right. A fluid does not have to be a liquid. Knock on it goes. Fluid does not have to be a liquid. It is a substance which flows. So what generally, which states of matter are fluids? When your doctor says you need to drink more fluids, he does not mean anything that flows. He does not mean gasoline or benzene or water or beer. He means what? He means water. But in physical sciences, not in medicine, but in the physical sciences, a fluid is anything that flows. So what two states of matter would probably fit into this? That's not a state of matter. What two states of matter fit into fluids probably? Liquid and gases. Liquids and gases, usually. Liquids and gases, specifically. Sometimes we consider some really like particulate solid matter to be fluid depending on how it's behaving. For instance, like if I have a bucket of sand and I pour the sand, that's behaving in a fluid way even though it's a solid. But usually it's these two, liquids and gases. We start out this lesson by talking about two basic things, then we go on to three principles, and then if there's time we'll move on to the gas laws. But let's start out with this. Buoyancy. This was a vocab word. Define buoyancy for me.
Buoyancy is how the ability
of a fluid or a liquid or gas to let something flow.
Okay, yeah, to let something float. Is that what you said? Float. Yeah, it's the upward force provided by a fluid. Do we live in a fluid? You already know because of the question that we do. Do we live in a fluid?
There is a fluid.
Yeah. There's a fluid all around us. There's the gas. There's the air that's all around us. So, does the air exert buoyancy on us? Sure. Actually, you would. There's a certain amount of buoyancy, not very much, because the air isn't very dense, and buoyancy somewhat depends on density. But if you were in a vacuum chamber instead of in a room full of air, a scale would say that you weighed more than if you were in a room full of air, because the air is exerting an upward force on you. What if you were underwater, which is a denser fluid? Significantly less. In fact, it's not very. You can't like tread air. Like I can't just float up into the air. Birds can. Yeah, why can birds do that? Because they have wings. Could they do that in a vacuum chamber? No, because they have to have the buoyancy of the fluid to press against. But buoyancy is an upward force, and this is as opposed to what? Counteracts what other force? Counteracts
gravity.
Yeah, counteracts gravity. And remember, gravity, the amount of gravity acting on you is your weight. The amount of gravity acting on an object is its weight. And so buoyancy counteracts gravity, which is why if you're in a denser fluid, like water, you weigh less. You are able to tread water. You can just like sometimes barely move, and the water will buoy you up because it has a buoyant force.
Why does air rise in water?
Why does air rise in water?
It's light
Yeah, because it has a smaller what than water?
and density.
Yeah. Yep. Generally, denser fluids provide more buoyancy. Denser fluids provide more buoyancy. Well, let's talk about density. We had density at the beginning of the year, but let's review density. The equation for density is rho equals m over v. You remember this?
Yep.
Okay. Rho is like, Tim, you can look it up. We looked it up at the beginning of the year so everyone can see what rho actually looks like. This is how I draw it to differentiate it from. But if you look it up on the internet, it looks kind of like this, which looks like the Latin letter P. But rho is a Greek letter that we use to represent density. Your book uses capital D. It's the same thing. I mean, it doesn't look the same. But the reason I chose to use this is because in upper level physics, we always use rho for density. I don't want you to get. It'll be easier if you know it now than if you have to learn it then. Anyway, so rho, or capital D, is what? Density. Measured in, we'll talk about that in a second. M, lowercase m, is mass, measured in usually grams. We can use grams or kilograms depending on the density of. And capital V is, no, lowercase v is velocity. Capital V is volume, measured in, well, either cubic centimeters or milliliters. And one lovely thing about the metric system, about the SI, is that these two things are exactly the same. One, if you have a piece of water that was 1 centimeter on each side, a cube of water that was 1 centimeter on each side, that would have a volume of 1 milliliter. These are the exact same unit. That is not true in the English system with ounces and ounces. Ounces and, what do I mean, cubic inches. That's definitely not the same. So this is nice. And then density, if density is mass divided by volume, and it would be the unit. Well, it's a mass unit, grams, divided by a volume unit, cubic centimeters, or grams per milliliter. We can also use things like kilograms per cubic meter or kilograms per liter, but this is the most usual that we will use in this class.
So
That's how we calculate density.
well, how do you measure this? Not like, so like you say, mass is measured in grams, it's measured in milliliters. Is that?
Density would be measured in grams per milliliter then. Just whatever your mass unit was divided by your volume unit is the unit for density. Okay, now what if we have density and we need to solve for mass? How what do we call that when we do this to an equation?
M equals.
Manipulate. We manipulate the equation. So how do we, first, what do we have to do? If we're trying to solve for mass, what is the first thing we still have to do?
Yeah.
Write down what I call the raw equation. We have to write down the way it always is first, and then we're trying to solve for mass, so what do we need to do next?
Multiply by M.
No? Get volume over. So V times rho equals M. Good. So that's how we solve for mass. What if we're trying to solve for volume? No, be careful. What's the first thing? If the thing we're trying to solve for is in the denominator, what must we do first? This is my rule. We need to get in the numerator first. So it's still, our first step would be V rho equals M. And now we divide both sides by rho. So V equals. If you try to do it in one step, little freshmen are always getting the flipped equation, which is wrong. It's tempting when we see rho equals m over v and we want to get v by itself that we just multiply m over. And it feels like, well, v is by itself is what it feels like, but that's wrong. Because what you actually get is 1 over v. So do it like this and you'll be right every time. You'll be expected to do density problems on your test and also solve for other variables besides density. Do you have questions about this before we move on? Okay. Now let's talk real quick about what makes something float and sink. And the first thing you need to do to talk about that is talk about something called Archimedes Principle. So write this down, please. You probably already have this. Was it a vocab word, Archimedes Principle? Well, let's write it down. Archimedes Principle.
Archimedes was a Greek.
Archimedes was a Greek philosopher. Yep, a Greek philosopher. And the legend is, and this is probably apocryphal, which means this probably didn't actually happen, kind of like Newton and the apple, you know. But the legend is that there's a bathtub, and he got into the bathtub, and he saw that the water level rised up when he got in. He thought about what we call displacement now. And the legend is that then he jumped out of the bathtub, he shouted, or I have found it, and then he went down the street naked, telling everyone about how he had found what displacement was, which is something he'd been working on for a while, apparently. But I don't think that's true, or if it is, maybe he was also drunk. You never know with the Greeks. Okay, but what is true is that this is about displacement. This is about displacement. Which is that when an object is submerged, what's submerged mean? Under. Submerged in a fluid, the fluid level rises by the volume of the object. So basically, if you have a 1 cubic centimeter cube and you plop it into some water, the water level will rise by 1 cubic centimeter, or 1 milliliter. And then this has to do with floating. If the object has we're going to do two things, greater mass and smaller mass than the water displaced. Well, if it has a greater mass than the water displaced, what's going to happen to it, do you think? So say we have our object. Yeah, we have an object, and we place it in the water, and it displaces 1 cubic centimeter of water, because it has a volume of 1 cubic centimeter. 1 cubic centimeter of water has a volume of 1 gram, and if the object weighs more than 1 gram, then it sinks. And if the object weighs less than 1 gram, then it floats. And then this also relates to density, because basically, if the density is greater than water, it sinks, and if it's less than water, it floats. Okay? So put that in your pocket. Does anyone know the density of water? I'm going to tell you. Rho of H2O, the density of water, is 1.00 gram per milliliter. It's super easy to remember. So basically, if any object has a density greater than 1, it sinks. If it has a density less than 1, it floats in water. I don't remember the density of air, but that's true for air too. Can you think of something that floats in air? What kind of balloon? A helium balloon. A helium balloon, because in the same way, the helium balloon has a certain volume. We'll say a 1 liter balloon. That helium balloon has less mass than 1 liter of air, and so the buoyant force acts upward on it. In fact, the buoyant force always acts up on it, but in this case, it's greater than its weight, and so it moves up. The balloon looks like this. In the helium balloon, it looks like this. F sub B, buoyant force, is greater than F sub G, the weight, and so it moves up. Remember forces? Has a net force in that direction, and therefore it also accelerates in that direction. Yes, right.
So, like, what about, like,
Good, yeah. So ash, like a particle of ash, actually has a greater density than the air, but why is it floating? Like, why does it actually move up? There's some other things going on there. What force must be acting on it? So gravity's acting down. There's some air resistance, but also the air itself, when it moves, can carry things even that are heavier than it along with it. Like, for instance, like a sand particle, if there's a heavy enough wind that the fluid motion of the water or the air or whatever the fluid is can move that particle along with it, even if it's more dense than the surrounding medium. Good.
like, say you put a helium underwater.
Yeah, it'll float.
But since the helium tries to rise, would you even be able to get it under the water without the balloon popping?
Let's think of it this in a different way. If you have a helium balloon and a regular air balloon, they're both underwater. You push them under the water the same amount. You could get them both underwater. You push them both underwater and you're holding them under. Which one is going to have a greater buoyant force acting on it? Your acceleration. The helium. So which one will seem to rise up faster? If they race to the surface, which one's going to get there first? The helium. Same thing as like if you have a cork and an air-filled balloon. You ever been in the swimming pool and you put the ball under the water
Yeah.
and it shoots out? Like force acting on it. The buoyant force can be very large, and the longer it has that unbalanced force acting on, the deeper you get it, the longer it has an unbalanced force acting on it. So the greater the speed is when it finally breaches the surface. If you get it 12 feet under, if you can manage to put enough force on the ball to get it in the bottom of the 12 foot, it'll just rocket out of the pool when it gets to the top. Do it next time.
Theoretically, water cannon.
Water cannon, yeah. Have your enemies sit over top and watch, and then you can blast a hole straight through their body. Yes.
So how come even just blowing it below the surface doesn't create
It doesn't create a what?
like a lot of pressure? Like it doesn't.
Like a lot of buoyant force. It does, and you feel it when you try to put it under.
Yeah, so it's not like if you hold it longer there it won't be any different. If you hold it like a less.
It will. What happens is the force doesn't change. The unbalanced force doesn't change. But the further down you get it, the longer it has to rise up. It has this acceleration the whole time. It has this acceleration the whole time. And so remember that acceleration is changing velocity, and so every second that goes by, the velocity increases by this much. And so if it's 12 feet, or what is that, like 4 meters under, and every second that goes by, it's accelerating, its velocity is getting faster and faster. By the time it gets to the top, that's what's happening. It'll be going faster. Questions about that?
So like a free dive, when people free dive,
Yeah, without any air or whatever.
yeah, how far like does the human body able to?
I don't know.
Is it, like
Look it up.
36 feet?
Yeah, there's some. I don't know. I thought it was a lot deeper than that. I thought someone went like 500 feet down on a free dive, but I don't know. Look it up because
Yeah,
that does relate to this. Okay, I think the class is going to be dismissed. We didn't get all the way through fluid dynamics, so I'm going to title this video Fluid Dynamics Part 1, but since we didn't have time to finish, we'll continue it tomorrow. Do you have any questions about what we did cover? Density, Archimedes Principle, buoyancy. Bye.